This is our first topic on electrochemistry. So basically, we can break most of the words up in this topic. Electro to do with electricity or electrical energy. Chemistry, so we're looking at reactions. Two things that do not change no matter which part of electrochemistry we're looking at are the definitions of anode and cathode. Those are both electrodes, which means they are things that conduct electricity, and we normally put them in solutions or liquids for them to conduct the electricity through and into those liquids or solutions. The anode is always the one where oxidation occurs, and the reason that I've emphasised the first letter is they're both vowels, so that's a way to remember it. The vowels go together. The anode is where oxidation will occur. The cathode, consonant, is where reduction, also a consonant occur. All right, so you can use that idea there. When we do electrical cells, which is the other part of this, doing our electrolysis today, when we do electrical cells, the plus and minus swap over. So what we find is positive for this one is going to be the opposite electrode for cells. So just be aware of that. Again, we can break down what we're doing today, which is electrolysis, by looking at its word. Electro to do with electrical energy, either using or generating, it doesn't tell us that, but to do with electrical energy. And lysis is the breaking up of something. So lysis to do in biology is usually the bursting of a cell. It's part of the process of the life cycle of a virus, for example, where it bursts or lyses the host cell to release more viruses. Well, this is the lysis of a chemical, because we're talking about electrochemistry. So the breaking up of a chemical into its elements usually, okay, and using electricity to do this. So I haven't shown a complete circuit here, it's just for simplicity, really. The first experiment we did was we got some copper chloride and we put 2 carbon electrodes into those. Carbon because it's not very reactive and because it conducts electricity quite well. Okay, it's also going to have no effect on the outcome because carbon doesn't react with chlorine or copper very well at all. Okay, so when they become elements, there's not going to be a reaction there between them and carbon. And what we observed is that one of them bubbled and one of them got a coating of a pinky brown solid, which we inferred to be copper. We also tested the bubbles with some damp starch iodide paper, and because chlorine is more reactive than iodine, then the chlorine turned the iodide into iodine and went back to being chloride. Of course, iodine with starch is blue-black. So we saw that it went blue-black. That confirmed that it was a halogen. There's no fluorine or bromine atoms in this, so we know that it's got to be chlorine that's made. Okay. Just like in our previous parts of the topic, we need to be able to do half equations for these, and ultimately probably a complete equation. Copper chloride at the concentration we had, which is it was a saturated solution, has got very high concentrations of copper ions and chloride ions. Yes, there's also hydrogen ions and hydroxide ions from the water, but because this is saturated, these are the 2 most important ions. Okay. We saw this pinky brown solid, so we inferred quite correctly that that was copper. And we were able to see that the chloride became chlorine because of the effect that had on starch iodide paper. So all I've really got to do now is balance out the elements and the charge. So the coppers are balanced, I just need to have 2 electrons there. And 2 chlorides are needed for this, which means 2 electrons here. So then we have to use this transfer of electrons to decide which one's oxidation and which one's reduction, so we can decide which is the anode and which is the cathode. So before we can say which one's the plus and minus, let's just quickly put an R and an O there. This one's got electrons being added, or is going from an oxidation number of 2 to 0, so this one must be the reduction. So I'm just going to put an R there for reduction. And this one here is losing electrons, so it's oxidation. Now, which of those would be attracted to a positive electrode in the solution? Well, there we look at the charges of what we started with. We started with a chloride ion and a copper 2 ion. their charges give away what they would be attracted to. Opposites attract. So the chloride is attracted to the positive. The copper is attracted to the negative. So therefore, in this case, so in electrolysis, the reduction is happening at the negative electrode. So the negative electrode must be called our cathode. So those that know about batteries might know that the cathode of a battery is actually its positive terminal. So you'll notice that's the opposite to what you might know about batteries. Right? So our negative electrode is our cathode because that's where reduction, a consonant, is occurring. And therefore anode oxidation positive. All right. The next reaction we did was where we had some sodium chloride and we put some universal indicator in it and it went green, expected, pH of 7. But then after we did our electrolysis, we noticed there were bubbles at both electrodes, not just at one. We expected chlorine to be at one of them, same as this one, at the positive terminal. But there were bubbles at the negative terminal as well, or negative electrode. And that's a bit confusing. But that's where we need to look at what's present. Sodium, even if it was turned into sodium metal, would then immediately go back to sodium ions. Okay, because it's in a solution. Sodium metal doesn't stay as a metal in water. It goes back to being ions all the time. That's why it's so much fun to throw a bit of sodium into water, because it blows up, because it reacts so quickly to become sodium ions. So the sodium ions are not actually reacting. Not really. Okay? So therefore we have to look at what else is in that solution that might be reacting that's positive. And we've got hydrogen ions or hydronium ions because water has those. It doesn't have a lot of them. It's got 10 to the negative 7 according to our universal indicator. But as we did it, we noticed the pH got a little bit higher. Wouldn't let you do it for long enough to get it really high because it was chlorine gas being made. But the pH was going up. So that suggests that the concentration of hydrogen ions must be dropping. And that's what we observed by the pH going up. Because a higher pH is a lower concentration of hydrogen ions. So actually what it was making was sodium hydroxide. Because of course if it's water, it's got hydroxide ions as well. As I say, I didn't let you do it for long enough because of the poisonous chlorine gas being made. And I sure as heck wouldn't have let you have a naked flame near it because you're making hydrogen gas. So that's why we got those observations. And these are the two half equations for that. So although we didn't have HCl in our solution, we had those two ions present, so the two gases, hydrogen and chlorine, being made. So hydrogen gas was being made at its reduction, so at our cathode, which is our negative terminal, and chlorine gas was being made at our positive terminal, oxidation, so our anode. So in this reaction we have got sodium chloride reacting. We can see down here using universal indicator that it's neutral, but where it's reacting it's becoming a base. The reason for this is that the sodium ions are not actually reacting. It's the hydrogen ions reacting instead, so we're ending up with sodium hydroxide solution in here. This is chlorine being produced here, which is why we are doing this in a fume current.